Welcome to this lesson on working with arrays in MATLAB. In this lesson, you're going to learn about working with arrays and the application in MATLAB. Although this might seem basic, it is crucial that you understand the application of arrays in MATLAB. Understanding this lesson is fundamental to working with multidimensional datasets in MATLAB, which you are going to be learning in subsequent lessons. Let's look at the anatomy of a matrix. A matrix is made up of rows defined horizontally and columns defined vertically. The intersection of a row and column defines the address of each element of a matrix, or what we refer to as a cell, similar to what you have in spreadsheet. So this element is defined by the row and the column. There are two ways to access the address of any element in a matrix. One way is by using the row number and the column number. So this element is defined by row 3 and column 2. Alternatively, MATLAB supports linear indexing, where each element is numbered sequentially from the first column to the second column up to the last column. So the numbers in red defines the linear indexing from element number 1 to the 25th element in the matrix. The element in the blue box is therefore accessed by the row and column number or by the linear index. So P34, referring to row 3 column 4, is the same element as the 18th element of the matrix, which is 1. Now, a vector can be either a row vector or a column vector depending on the direction. So when you have a vector consisting of a single column, it is referred to as a column vector. So here we have 4 rows but just 1 column. Similarly, when you have a vector that is having just 1 row and multiple columns, we refer to such a vector as a row vector. So the vector in yellow here is defined as a row vector because it has just 1 row but 4 columns. So that gives us 1 by 4. Now we can have a subset of a matrix by defining a number of row and column. So for this matrix, we have 3 rows and 4 columns, which makes it a 3 by 4 matrix. In general, a portion of a matrix can be extracted by specifying the rows and column range. Generally, we have the sub-matrix is given as matrix R1 to R2, defining the range of the row as well as defining the range of the column. In this case, R1 and R2 specify the beginning and ending rows, while C1 and C2 specify the beginning and ending columns to be extracted to define a new matrix. Welcome to the lab section. Let's practice working with arrays in MATLAB. To start with, let's create some basic matrices. In order to combine M1 and M2 row-wise in a process called concatenation, we can define a new matrix called M R to represent row-wise. Okay, so we combine M1 and M2 row-wise by defining M1 and M2 in similar way. We create a row matrix. So the command mr equal to M1 space M2 concatenate, that is combine M1 and M2 row-wise. To combine M1 and M2 column-wise, let's define a new matrix MC representing M column-wise. This will be M1 semicolon M2. So this combines M1 and M2 column-wise. In order to define the size of a matrix, we use the size function and the name of the matrix, say M1. This gives us the row and column of the matrix. Let's see the size of MR. So we have 2 by 4. Remember MR, 2 rows, 4 columns. To create a copy of a matrix, you simply define the new matrix, say M copy, and assign it to the matrix you want to copy. So M copy stores the same matrix as M underscore C. Let's practice how to specify all the elements of a row or column of a matrix. To do that, let's create a new matrix. M has magic 4. The magic function creates a special square matrix where the sum of the columns and the sum of the rows are equal. To specify the first column of M, we use let's call this M1 equal to M, all the rows, comma, the first column. Remember, the first index represents the row, the second index represents the column. So by using the column operator in the position of the row, we are implying all the rows, and then the 1 here represents the first column, column 1. So this gives us all the elements in the first column. Likewise, if we want all the elements in the third column, we can simply type column 3 to be M, all rows, and then column number 3. So this gives us all the elements in the third column. In order to specify all the elements in a row, we can call this R1 to represent row 1. That will be M. Here we have the first row. In the position of the column, we specify all the columns. So the 1 represents the first row, and the column operator represents all the elements in that column. So this gives us all the elements in the first row. So let's clear our command window in order to have more space. So we can call back our matrix M. So to specify the second row, we simply say row 2 equal to M, the second row, or the column. The end keyword is used to represent the last row or the last column of a matrix. In the case of a vector, the end keyword is used to represent the last element of the vector. Let's assume we don't know the total number of rows or columns of a matrix. We can use the end keyword to access either the last row or the last column. To do that, let's create a variable called rEnd to represent the last row. So we can call the matrix M. We use the keyword end in the row index position, and we use a column in the column index to represent all the column of that row. This will give us the last row of the matrix. Let's assume we also want to get the last column of the matrix. We'll create a new variable called rcolumn equal to m. We want all the rows with the last column. So this command will give us the last column of the matrix M. Alright, let's try subscripting a matrix, in other words, to get a section of a matrix. So we can call a variable a1 to be m. We want the first two rows of the matrix. So this will give us the first two rows. So assuming we want the first two rows, but just for the first two columns, we can then define a1 to be m. We want the first two rows and for the first two columns. So this will give us the element 16, 2, 5, 11. Okay. Alright, let's have some more examples. These denote all the elements in the first and second row that are also in the first through the third column of the matrix M. So we have elements in the first and second row all through from the first to the third column, which is basically from 16 to 3, from 5 to 10. So let's run this. So we have the element in the first and second row, and then the first to the third column. So let's assume we want the elements 6, 12, 15, and 1. That will be the elements in the third and the fourth row, but for the third and the fourth column. So that will simply be, let's say, A3 equal to M, the third through the fourth row, likewise the third through the fourth column. So that gives us the element in this position. Basically, that is the idea of how to subset a matrix. So let's assume we want to display all the elements of the matrix M from the first to the last element. Let's assume we want to display all the elements of the matrix M from the first element to the last element. We can simply create a new matrix, so M. So this will display all the elements of the matrix M as a vector. So we have them sequentially from the first to the last element. So let's try using the end keyword. Since V is a vector, we can call that V1 equal to V end. As you can see, this gives the last element of the vector V, since V is a vector. Alright, let's clear the command window once more. It should be noted that MATLAB also supports a form of indexing that uses one array as input for another array. So recall M. Now remember our linear indexing, so this is element number 1, 2, 3, 4 up through 16. Now let's assume we want to get every third element of the matrix M from the very first element. We can decide to say okay, K equal to 1, step 3 up through Alright, so this is K starting from 1 step by 3 up to 16. So this gives 1, 4, 7, 10, 13, 16. So from the matrix M, 1 represents the first element, the fourth element, the seventh element up through 16. So for we to get the element of M at this position, we can simply create a new matrix. Say M K. So this will return the element at this position of the elements of K, which is 16 for the first element, 1, 2, 3, 4, 7, 10, 13, and the last element 16. You can use another array as input for another array. Let's practice removing elements from an array. Assuming we want to remove the third column of the matrix M, we can simply say M. Third column means all row, third column. Assign that column to an empty array. So this automatically removes the third column and create our M as this. Assuming we want to remove the first row of our M now, we can simply say M, first row, all the columns to be equal to an empty array. So this removes the first row. So it's actually possible to remove elements of an array. And you can also assign specific elements of an array new values. For example, let's assume we want to assign this to be 0. This is the element in the first row, the second column. So say M first row, second column should be 0. So this automatically replaces the element in this position by 0. A range of values can also be replaced. So let's assume we want to replace 5097 by -1. So 5, 9, this is first, second row, first, second column. So that's M, first to second row, first to second column, assigned a value of -1. Automatically they are assigned and replaced by the new value -1. In MATLAB, it is also possible to carry out logical indexing, whereby you search for elements that satisfy a particular condition. To do that, let's create a new random matrix. Matrix of random number 4 by 4. Let's assume we want to search for all elements that are greater than 0.5. There are two ways to do this. The first way is to create another array, a logical array. Let's say B equal to A greater than 0.5. This will return a logical array showing elements that satisfy the specified condition. The condition here is A to be greater than 0.5. So the first element here, 0.2599, is less than 0.5, so it returns 0. Likewise, the element in this position is less than 0.5, so it returns 0. 0.8693 is greater than 0, so it returns 1, showing true. Similarly, this satisfies the condition, so you have 1. Now, with the logical array created, we can decide to create a new matrix showing elements of A that are greater than 0.5 by using B as an input. So this will create a new matrix showing elements greater than 0.5. Alternatively, we could also combine the two processes together and say A greater than 0.5. Okay, we have the same result, showing all elements of A that are greater than 0.5. Okay, so back to our matrix A. Let's assume we want to assign all values less than 0.5 a value of none. We can simply say A less than 0.5 should be assigned none. So automatically all values less than 0.5 are assigned none in the matrix A. So this is how you apply logical indexing. Let's try another example. We create a magic matrix P 4 by 4. Let's assume we want to look for all elements of P that are prime. So we can create a new matrix Q equal to is prime P. So this will create a logical array showing all elements of P that are prime. So all elements of P that satisfy this condition are assigned the value of 1, else the value of 0. So 16 is not prime, so it's 0. 2, 3, 13 are all prime numbers, so they are assigned here. So assuming we want to assign all such prime numbers a value of none, we can now simply say P of Q equal to none. So this will assign all prime numbers in P the value of none. Let's practice how to reshape a matrix. A matrix can be reshaped based on its row and column and the total number of elements. Alright, let's create a new matrix. Zip M equal to 1, 2, 3. Let's see the size of M. Okay, so M is 4 by 3, meaning we have a total of 12 elements, which is 4 times 3. To reshape the matrix M, we can reshape it to 6 by 2, which will still be a total of 12 elements. So we can create a new matrix M reshaped and we call the reshape function M as input, and we define the new shape for M. So this will reshape the matrix M from a 4 by 3 matrix to a 6 by 2 matrix. We could also reshape this to a 2 by 6 matrix. Now, since the total number of elements in the matrix M is 12, if we try to reshape, say MS, to, let's say, 5 by 3, MATLAB returns an error telling us that the number of elements must not change. So since we have 12 elements when you reshape, the total number of elements must be maintained. So this is not feasible. We can reshape M to be 4 by 3, 3 by 4, as long as the total number of elements is 12. Alright, let's look at some additional array function. Recall M. We can decide to flip the matrix M from left to right. So if we call that F flip from left to right matrix M. Okay, so this is flipped. 3692 is now on the first column. This is on the second column, and this is on the third column. You can also decide to flip the matrix up to down. So let's say up, down, equal to flip up, down, matrix M. So this will flip our matrix M up, down, meaning the last row becomes the first. Likewise, the third row becomes the second. So the matrix is flipped up, down. This is applicable when you have data that are arranged from north to south, and you want to flip the data such that they are arranged from south to north. We could also decide to sort the elements of the matrix M, so they are sorted accordingly. We can decide to find the sum of M. This will give you the sum of each of the column. In order to get the sum of the rows, you must tell MATLAB to sum along the second dimension. This returns the sum of the rows of M. Okay, recall M. So 1 plus 2 plus 3 is 6. 4 plus 5 is 9 plus 6 is 15. 7 plus 8 plus 9 is 24. 4 plus 5 is 9 plus 2 is 11. So that gives you the sum of M. We can also decide to find the minimum value of M. So it returns the minimum value along each of the column. You could find the maximum value of M. This also returns the maximum value along each of the column. So in order to get the minimum for the entire matrix, you can decide to say the minimum of matrix M. So this returns 1. Okay, because the first minimum gives you the minimum along each column, while the second minimum will give you the minimum of that output. Likewise, the maximum of M gives you the maximum element of the matrix M. Let's try looking for the maximum and minimum value of a vector matrix. So assuming we create a new matrix V, so we create a new matrix V using all the elements of matrix M multiplied by 2. We can use X equal to K equal to minimum value of V. So this will return the minimum value and the index of that value. So here we have the minimum value is 2 and the index is at position 1. To look for the index and the value of the maximum value, we use max. So this will return the maximum value and its position. So if you look at matrix V, the maximum value is 18, which is at position 11. Feel free to practice working with arrays in MATLAB. In subsequent sections, we're going to learn about working with multi-dimensional arrays and the applications to various scientific datasets. Don't forget to hit the subscribe button, like and share this video.